Buen día. En nombre de la Asociación Mexicana de Industriales de Acabados Superficiales, quiero agradecer su interés en nuestros programas de capacitación. La necesidad de oportunidades educativas en México para nuestra industria fue uno de los principales factores que nos impulsaron a crear AMAS hace más de 5 años. En AMAS, creemos en la educación accesible y de calidad y estamos convencidos que es a través de esta capacitación continua como podremos ser los líderes en nuestra industria. De parte del Consejo Directivo y equipo de AMAS, espero que saquen el máximo provecho de estas capacitaciones. Les doy la más cordial bienvenida y les recuerdo que en AMAS estamos para servirles.
Good day. My name is Brad Durkin. I work for Coventya, Inc. I'm the director of the International Product Management Group for the company. Today, I'm here to talk to you about how to successfully anodize cast aluminum alloys for higher performance. It's known that anodizing, the technique of building an oxide layer on aluminum, is considered a green technology that provides very good corrosion, wear, and other properties for aluminum alloys for over 75 years. This webinar today will cover some new process development on how to successfully provide good anodic oxide layers on cast aluminum alloys, which have always been a problem for applicators to have success. This is my biography. I've been in the industry for 38 years and have a wide range of experience. I'm involved in many of the associations for our industry, including NASF, technical chairperson for the Technology Advisory Committee. I'm a member of ASTM and many other societies with a lot of experience in different areas of coatings and applications. This webinar has a lot of credits to many people at Coventya who share in the contents of what is here and continue to work to provide very good process systems for our customers. Our research and development team in Turkey and the deployment team in Europe have spent the last 3 years developing this process to be able to successfully process cast alloys with anodizing oxide layers. Here's the background on Coventya, including more information that can be found on the internet about our company. Coventya is the top 3 global technology suppliers for surface finishing processes with a global footprint that covers more than 60 countries on 5 different continents. Coventya has a technology portfolio that starts at the surface preparation of metals, light metals, and non-metals that include plating on plastics, also conversion coatings, and anodizing all types of parts and components. The difference for Coventya is the fact we also have a water care division that helps manage the considerations for waste treatment of technologies under the development in the initial stages. As a global supplier of surface finishing technology for all industries and applications, as shown here, our leadership in technology for supporting the automotive, building, furniture, the plumbing, sanitary, fittings industries, the energy sector with technology for meeting high performance demands in the data storage industry that are used in computers, TVs, and other electronic components. So I'm happy to be here today, coming back to the webinar to talk about how to successfully anodize cast alloys and what was the motivation for the development process of this technology. We see many industries changing and evolving over the next years. Next to iron, aluminum is the most widely used engineering metal in today with increasing demands. Many good properties, including the formability and the manufacturability of parts. It offers high corrosion performance with proper coating applications, of course, and it's got a low weight to high strength of properties that give the background for its consideration and use across many different applications. For meeting many types of high corrosion performance demands, the proper preparation for any coating application is critical for the success for the wrought alloy types, but also especially important for cast alloys, which is the consideration today when we talk about anodizing. The growth of the use, especially in the automotive sector, is expected to be increasing through 2025 because of the need for reduced weight in these vehicle systems. Over the next decade, North America alone is expecting a 39% increase in the use or the consideration of use for many different types of applications. Especially with the electric vehicles, EV vehicles, the growth of that market demands lightweight options instead of the use of steel, because the battery systems offer a lot of weight to the cars that must see reductions in other areas. This slide is very interesting because it shows where aluminum comes from and why does it offer so much important significance. Well, aluminum comes from the mining from the earth of a mineral called bauxite. The bauxite minerals are then converted to alumina oxide, and then it is melted into aluminum metal, which is cast into aluminum ingot bars that will be turned later into aluminum alloys. Going from metal to alloy, once the aluminum metal is cast into ingots or bars, they are shipped to process foundries or other part manufacturers. There, they are remelted so other metals can be added to them that provide the wide range of engineering properties. The addition of the metals create the different types of aluminum alloys that are used on all types of industrial applications. The type, the blend of the metals added determines if the aluminum is considered a wrought alloy or a cast alloy, which is an important reference to the way that the parts are made. Wrought alloys are made into bars and other shapes, or even coils of flattened, rolled up aluminum. Cast alloys are just that. They are put in the casting process to make the parts. Later, we'll discuss how the casting process does have an influence on the surface finishing processing. The metals that are added to the aluminum provide the final set of properties that they can achieve, but the metals added do have other important considerations in surface finishing applications. That's what makes it difficult for applicators in many cases. You can see, in addition to aluminum, the primary alloy constituent in the highest concentration determines the type of alloy that's referenced. For example, by saying 2000 series, we see that it contains higher concentrations of copper. Or for a 5000 series alloy with high magnesium. Again, these metals provide a range of strength or other engineering performance properties that are important to the alloy. But all these different alloys have defined properties and uses for many applications. Generally speaking, the wrought alloys as shown are much easier to surface finish with plating or anodizing or even conversion coatings compared to cast alloys, which offer difficulty. As shown, cast alloys offer many engineering benefits over the wrought alloys. They continue to offer low cost to produce, high production output of complex shaped parts, and that's why they're often used in high manufacturing applications. But they are difficult to surface finish. The silicon and the copper metals added to make castings must be taken care of in the processing before anodizing. The casting methods used to make the cast alloy parts also have a significant impact on their performance, but generally they're more challenging to process in surface finishing, and that's why we have difficulty. That's why we've developed processes that deal with the cast constituents. So depending also on the casting method, will give a high surface roughness or even greater porosity of the cast alloy. And so that offers additional challenges when we talk about surface finishing technologies or methodologies that are needed for successfully anodizing these cast alloys. As shown here in the photographs, all types of lightweight and complex geometry parts and components can be easily manufactured using casting methods or casting alloys that meet functional and decorative types of performance applications. What makes it possible to create such complex shapes? Well, that's the next question that we must answer. Silicon is added to cast alloys for allowing better casting of parts, components, and for manufacturing complex configurations. Its concentration will vary depending on the type of cast alloy, but also the casting methods that are used to make the parts will also change the nature or the shape of the silicon at the surface. This, generally speaking, provides one challenge in surface finishing cast alloys that we must overcome. But remember, please do not confuse silicone with silicon. The E in the name does make all the difference in this case. Remember, silicon is an element on the periodic table, while silicone is a chemical compound. They are not the same. During surface finishing operations, not only the concentration of the silicon that's added into the alloy is important, but the actual orientation of the silicon or if there's any concentration gradients because of a tempering process during the part manufacture becomes really a concern for the applicators. And it's difficult to overcome to make quality oxide layers. Remember that when we're anodizing or creating an oxide layer, we're dissolving the aluminum, which happens to be the metals in the alloy that causes problems too. So we have to overcome these. For example, copper is a concern in these alloys because you get copper smuts. And the silicon smuts that form can be difficult to remove before the anodizing process. And that's the difficulty in taking care to manage the silicon so that we can successfully anodize these alloys. The engineering reasons that cast alloys are used are driven by performance. But as already noted, the coating process is very difficult and a challenge unless we take some considerations for their processing. This is why we have developed different types of surface preparation methods for different types of high silicon cast alloys. You should avoid alkaline etching these castings because the complexity of the smuts that form on the surface can be more difficult to remove. However, sometimes alkaline etching is really needed for some pressure cast alloys or forgings in this case because they do create different smuts, but you have to etch them in a different way. Generally speaking, it's best to stay with an all-acid process cycle for cast alloys, with the exception of first mild alkaline cleaning. Many anodizing applicators follow the military specification for applying anodic oxides on aluminum and alloys. The specification MIL A8625 recognizes that there are issues traditionally in trying to process cast alloys in their section 3.6.1.1 as it references cast alloys there. It's stated that dyed aluminum castings may show slight variations and lack of color coding uniformity. Well, the degree of non-uniformity acceptable shall be established by the procuring activity. The translation here means the cast alloys will not provide the same results as wrought alloys with traditional approaches to anodizing, and that's why a new process approach must be taken for their consideration of quality, high quality types of coatings. The casting alloys were originally not designed for surface finishing. Their engineering benefits to the parts were important, and the first considerations, including the ability to make complex shapes apart at low costs and high production manufacturing throughput. So that causes difficulties when we start talking about surface finishing applications. So with castings, the traditional experience in our industry, the thought of providing a robust finishing system is the secondary thought when the engineers use cast alloys. And it was up to the surface finishing applicators to figure it out. So this is what Coventya has done. We've been able to figure out a process methodology that provides anodizing oxide layers with high quality on high silicon cast alloys. These are the more common cast alloys that we see for surface finishing requirements. This represents a small portion, but the point here is that not all cast alloys are alike, and the method of casting, as well as the alloy and the resulting orientation of silicon within the alloy, will impact the success or the failure for any coating application. As you can see, the higher the silicon in the alloy, the more difficult rating is shown to process, not only for anodizing, but we include plating and also chemical conversion coatings, which is not commonly attempted for castings because of the poor results with corrosion performance. Today, with the research and development work from my company has completed, we have a remedy for processing high silicon cast alloys with anodizing. We must look at the viability of the casting itself and the amount of silicon that's in the alloy, but anodizing with success comes considering two different stages of processing. With success, the market can meet the new demands for providing to the automotive industry a solution today for reducing weight in vehicles by replacing heavy steel castings with parts fabricated from cast aluminum. This is a new era that we look forward to being successful. For the next decade, we see greater focus on lightweight construction for the vehicle market, which is driven by the electric mobility. Battery systems in the EV cars provide a lot of weight, And so for providing long-range operation of these vehicles, we must look at alternative lightweight materials for parts and components. High corrosion performance and also the decorative characteristics are also required for filling these industrial needs. In the 1970s, 75% of the vehicle was constructed from steel, as shown here, but this share has now fallen to 50%, and by 2030, its share is set to fall to 13%. So the requirement for weight reduction to reduce carbon dioxide emissions has also led to the introduction of aluminum and magnesium construction materials that we will continue to see increases in use. By 2030, the use of lightweight materials will increase to 67% of a total material for the average automobile. This is why we need new coating systems. As shown in this slide, here are some examples of the types of parts that are currently or that will be constructed from cast aluminum and that will require some very good capability for anodizing successfully with these types of components. Traditionally, we know why cast alloys were being avoided for anodizing processes. They were easily etched, they had the formation of the complex smuts that would result from the wrong processing. Remember, in traditional anodizing, the processing sequences that would include alkaline etching, and they would cause complex oxides that would cause smuts, which would cause difficulty for creating the oxide formation on their surfaces. So we've had to develop special types of alkaline etching formulations, also acid etching formulations for these. Some examples of defects common for castings included low thickness, what they call zero spots, with a greater tendency for burning the anodized oxide layer, resulting in inadequate pore structures, which in the end, the pore structure for anodizing is the most critical part to provide high corrosion performance, to get good appearance and decorative performance from these alloys. Performance issues that have traditionally resulted from these three problems include poor sealing quality, equated to low corrosion performance, inferior die quality, poor color retention, both during and after the processing, and in use out in the application, the color would fade, which was poor resistance to the environment. These were all problems that needed to be overcome with looking at an improved process. In the next part of the webinar, to understand how the anodizing cast alloys work, we'll do a quick review of some anodizing basic principles so that we can understand how these processes will work. For the creating of anodic oxides, here is a nice graphical illustration of what happens to an aluminum surface during an anodizing process in a traditional sense. So it's always important to clean the surface, then etching of the surface is done to remove surface defects. During the etching, the alloy element smuts form. This is the difficulty with cast alloys and the reason why desmutting the surface is very critical for allowing the anodizing process to build the proper oxide and the pore structure. The sealing process for the anodized surface is very critical for corrosion performance. If the anodic oxide is going to have a color, then the dye absorption, provided the color, is a critical part of the sealing process. In comparing anodizing versus plating, for the creation of the anodic oxide layer, it actually involves dissolving the aluminum while also creating the oxide layer into the aluminum. This is much different compared to plating or a conversion coating that provides a coating over the aluminum. The oxide also has a greater volume or dimensional growth. So both types of mechanisms work. Dissolution of the metal, then growth of the oxide, which is important for the part dimension. If you have to worry about reworking parts, the stripping and rework poor quality anodized parts has many dimensional considerations. So getting the anodizing process right the first time is a critical success point of doing the process properly. Here is a roadmap for the anodizing process for aluminum. Considering cast versus wrought alloys, the etching chemistry, as I said, is very important and critical, and we must have a different approach or a special type of etch chemistry. For cast alloys, using an acid conditioning and brightening with acid etching is very important, while trying to avoid using traditional caustic etches which create complex smuts on the surface. The desmutting chemistry also must be sufficient and designed to be removing the complex smuts of copper and silicon. Without doing this properly, the creation of the anodic oxide will not be formed properly, and we will have inhibited surface thickness, which causes all kinds of different problems. That will be discussed more in the webinar. When talking about type 2 or type 3 sulfuric acid anodizing, here are the typical operating conditions for the process of creating the oxide layer, shown on the screen. Wrought alloys are processed with relative ease and anodizing applications. Paying attention to the operating parameters and using the correct chemistry electrolyte is shown in the desired properties of the resulting layer will give you high quality coating. So excellent performance for the intended application when we talk about the hardness, wear resistance, thickness, the color, stability, as well as the surface smoothness, amongst other properties. As shown in the slide, for anodizing aluminum, there are many beneficial properties that result. But it's important to remember that a key difference to plating is that the anodized oxide coating becomes integrally bound into the aluminum metal substrate. It's unlike paint or plating that requires a different type of bonding mechanism closely related to the surface. Today, anodizing offers a green coating application, and it's recyclable and generally considered safer for health. So there are many benefits for having a successful anodizing oxide process for cast alloys. So next in the webinar, what are the challenges for considering using cast alloys for anodizing? Well, OEMs and tier 1 suppliers want to use cast alloys in part and component applications. They are less costly because of the high output of part production. They can create complex shapes with many types of engineering advantages, but the ability to provide a high quality, performance-driven coating has not been really achievable until now. So Coventya accepted the challenge 3 years ago to provide a robust process for anodizing cast aluminum while also targeting these high silicon alloys. So let's see how to overcome the challenges of providing high quality anodizing for this range of alloys. So how to anodize cast alloys successfully? Well, the output for this comes in 2 stages. The first stage is to re-engineer the thinking and the application of the cleaning and preparation of the cast alloy substrates. It's very important to avoid creating complex smuts that are difficult to remove from the surface. The fact that the formation of the anodic oxide process dissolves aluminum, but also grows dimensionally into the aluminum must be an important consideration for the final roughness specification or the brightness specification of the coating itself. This is why we've developed surface leveling and brightening components, but these are also reasons why there are many options to the cleaning and the preparation of cast alloys prior to anodizing successfully. The second stage is to optimize the sulfuric acid anodizing electrolyte, and this is done with some new additives that are incorporated into the solution that provide a range of benefits, but primarily focused toward creating and developing a pore structure that is similar to what we can easily create on the wrought alloys, while also limiting the attack of the sulfuric acid electrolyte on the casting alloy, which is detrimental to the formation of the proper anodic layer. Traditionally, these examples in the list as shown are many reasons why cast alloys have been avoided for processing through sulfuric anodizing processes. Poor dye quality, poor color retention, burning of parts have always been a problem. It's actually the high silicon that causes the anodizing to have these tendencies for burning or low thickness spots that cause coating performance issues. So the ability to process to overcome the impact of the silicon in creating a thicker anodized oxide was the target for success. This also helps us for improving the sealing efficiency, the dye absorption, and the retention of the color for the cast alloy has been very critical, and especially when we talk about success of the process. This slide is a good general overview representation of the 2 stages that are needed for successfully anodizing cast alloys. In the first stage, we've introduced a new surface acid preparation process that demonstrates some improvements with the removal of the silicon intermetallic zones that exist in the layer and throughout the surface. In stage 2, we've developed some new organic additives in the sulfuric acid anodizing chemistry that help overcome the difficulties with the silicon. Only using the additives in the anodizing process does improve the performance of the thickness layer and the oxide layer, but for a greater density, harder, more uniform process, we need to incorporate stage 1 and stage 2. Here, the oxide growth is enhanced and a continuous coating can be obtained. The silicon intermetallic particles are activated in the stage 1, and then the chemical potential of the surface is changed. Bringing the chemical potential of the aluminum and the silicon together enables the anodizing process to continue more homogeneously over the part surface, where we get thicker layers. Depending on the aluminum alloy and the surface condition of the aluminum casting, the final requirements for a given color or the visual appearance of the casting needs to be determined which products are required. So in rare cases, would we need 5 preparation stages, but with high quality demands for some applications, some types of cast alloys, we have a full toolbox available to process all ranges of high silicon cast aluminum with stage 1 and stage 2. Remember, in creating the anodized oxide layer, we're dissolving aluminum, and where we are having higher concentrations of silicon in the formation of the proper type of oxide layer inhibits that. So unless we do something different to overcome the high silicon concentrations in the surface, the anodizing will not be successful. As previously noted, cast alloys must have a different approach compared to wrought alloys. The casting quality plays a very critical role in the success of the failure. We must avoid traditional alkaline etching chemistries, and the desmutting choices that we use are critical because the complexity of the cast alloy smuts are going to be different than they are for wrought alloy smuts. Some pressure cast alloys require alkaline etching considerations, and compared to gravity casting, we tend to favor acids in that particular application. The silicon concentration is one concern of cast alloys, but the type of casting process, or better stated, the method of the casting for the parts, does influence the anodizing oxide performance, which is another important variable that we have to consider. We have some data later in the webinar that will demonstrate the impact of the casting type on the performance of the oxide layer. For more focus on the functional anodizing applications, those that don't require high brightness, high color surface finishing, we have less steps required in stage 1. But where there's a greater focus on decorative appearance, performance related to decorative appearance, we have more steps required for stage 1 processing. The right surface preparation choice becomes very critical to account for the silicon in the alloy. The acid conditioning step helps to change the condition of the silicon, and it allows the anodized oxide growth to occur at 30 to 40% increase in thickness versus not using the application of the acid preparation step. We have developed these new acid treatment activations applied during the processing that helps to manage the silicon in the surface layers by decreasing their size and their shape, and it allows the anodized to grow more uniformly, but also without causing the formation of the complex smuts on the surface. So the deoxidizing step is simpler and more straightforward to have success. As shown in this slide, with the anodizing of 10% silicon with success, the importance of stage 1 steps are considered. In the top example, the traditional cleaning with a non-etch cleaner, brightening chemistry, and desmutting followed by the anodizing does not produce a good result after 800 hours exposure to neutral salt spray. In the bottom right photo example, the important incorporation of the special acid activation step manages the negative impact on the silicon and on the surface, and the result here is that there's no corrosion after 800 hours of neutral salt spray. That's why we say that stage 1 and stage 2 considerations are very important. For stage 2, once the proper preparation considerations are implemented, the creation of the anodic oxide takes place with improved efficiency. So let's talk about some of these details. One of the initial problems in the development of a successful process for anodizing the cast alloys, it was our ability to actually see the differences with the pore structure. So we've had to develop some specific techniques to be able to see in cross sections how the pore structure formation changes with these additives inclusion into the sulfuric acid anodized solution. Shown here, some special cross-sectioning techniques were developed, including defining the angle of surface sectioning and using some polarized imaging in these to see the different alloy elements and also the pore structure, considering their shape, their size, and their orientation in the alloy. Being able to see microscopically what was going on was very critical for us in a roadmap for the development of the chemistry in the sulfuric acid anodizing electrolyte. The additives we designed to work to modify the oxide microstructure by increasing the number of smaller pores, packing them in a tighter, more consistent order, offers better defined, more homogeneous, uniform structure. That's very critical for the overall success. We achieve a higher oxide surface gloss. We get a smoother surface finish of the oxide layer, which contributes to improved anodized functionality of the surface. That includes wear performance, hardness, and surface finish, including the brightness and the smoothness. The additive system helps to control the aluminum dissolution, and it minimizes the attack, which is very critical to avoid complex smut formation during the formation of the oxide anodic layer. As shown in this slide in the two photomicrographs at the same magnification, there is a much different oxide thickness and formation of the anodic oxide layer comparing the use of a cast alloy stages 1 and 2 compared to traditional processing in attempts to anodize the surface. In sample D, the resulting oxide layer has improved density while also incorporating the metallic silicon particles into the oxide layer instead of them causing disruptions in the formation of the oxide. As shown here, the additive package to the sulfuric anodizing chemistry function acts to depolarize the silicon. Basically, it improves the solution conductivity while helping to remove the heat at the part surface that's generated during the anodizing process. The result seen here in this electron dispersive energy spectroscopy mapping technique of the cross-section of the aluminum oxide interface shows how the destabilized silicon intermetallic particles now become incorporated into the oxide layer instead of limiting the formation of the oxide, which would normally occur without using a stage 1 or a stage 2 cast alloy approach. In looking at even higher silicon containing alloys, in this data set shown on the slide, different cast parts were evaluated for anodizing quality after following the cast alloy approach, looking at two different casting approaches, including castings from the pressure cast and those from gravity cast. As the data shows, the impact of choices for stage 1 and stage 2 will have on the oxide thickness and the hardness. As shown in the red box for the 10% cast alloy case, including only the additive package to the anodizing solution, slightly improves the ability of the oxide to form a thicker layer versus the baseline attempt without the cast alloy approach to the anodizing process. In this slide, we're showing a cross-section photomicrograph of a 10% silicon intermetallic cast alloy that doesn't have any special processing. So you can see on the left side, the anodic oxide can only reach 2 to 4 microns. For the right photomicrograph, the cross-section shows an anodic oxide from 12 to 18 microns simply by incorporating the stage 2 processing with the additive package for the anodizing electrolyte. In the case, we see up to 5 times greater oxide thickness compared to using no additive at all. Furthermore, in the next series, incorporating some of the stage 1 acid activation step with leveling to improve the surface finish, further doubled the oxide coating formation from 12 to 18 microns up to 25 to 30 microns, and further increased the oxide up to 45 to 15 microns with increasing the additive concentration to the anodized solution. So for the 10% silicon intermetallic cast alloy, using both stage 1 and stage 2 processing with the proper selection of stage 1 activation and the leveling chemistry demonstrates the advantages of incorporating both stages into the processing of the high silicon cast alloy. This also maximizes the oxide hardness, which is shown to be more resistant to abrasion. As shown in this slide, with increased oxide thickness and a much better defined, more uniform pore structure ranging from 24 to 26 nanometers, shown at 200,000 times magnification, the ability to provide higher performance with depth of color, range of color, shade of color that will have improved resilience from the improved hardness. There's less fading out of the color both during the processing and while the part is in its final environment, offers many benefits for high silicon cast alloys. In this slide, we do say pictures speak louder than words. Now, especially high silicon cast alloys, in this case, a 10% silicon concentration can provide improved appearance ranges than what was possible in the past. Because of non-disclosure agreements with our customers, we're unable to show full parts processed with the cast alloy process, but you can see here the depth of blue color is very impressive. In this next slide, coming back to the next data set, seeing how the casting method affects performance is important. The types of casting methods should also not be ignored when speaking about any cast alloy process. The manufacturing of the cast part does matter, and a reason why working with OEMs or tier 1 suppliers becomes very important for realizing a successful application. Here, as shown in the red box, the data comparing A10 to A40, pressure cast alloys do have some limitations with oxide growth versus a gravity cast part, but still the incorporation of the acid activation and the leveling steps in the stage 1, while also increasing the additive package to the anodized solution, does maximize the ability to provide a much improved anodic layer to the pressure cast alloy. We cannot emphasize enough that understanding the impact of the casting method will always have an important consideration in the success of anodizing cast alloys. As shown with the data for a 12% silicon intermetallic with stage 1 and stage 2 processing, we can demonstrate the improved oxide thickness and improved pore structure does have a very positive effect on the impact of the dye color as shown here in the following photomicrographs. We limit the leaching of the color during the post-rinsing. The processing of the anodized cast alloy compared to the different options in the cast alloy process can be shown in this different slide. So let's try to summarize some of the benefits that we see with the cast alloy approach of stage 1 and stage 2. As shown in this slide, it becomes very important to restate how important knowing or having some control over the casting process is critical for the success to process cast alloys with anodic layers. Working with an OEM or a tier 1 supplier who have good relationships with cast manufacturers who actually do the casting would be very greatly beneficial to the success in this case. If there is no control over the casting process or even input to the source of the casting that will need to be anodized, there will be inconsistency, quality, and other issues that will cause unacceptable results from the anodic oxide layer. So what does that mean? For a job shop applicator, it will be very challenging to consistently produce very high quality on cast alloys without some close relationship to the cast alloy manufacturer. As an example, receiving some 7% cast alloy from 2 or more casting sources might require some modifications to the stage 1 surface prep. And as shown previously, there might need to be some additions of chemistry to make the process more successful. This is why consistency of the castings are critical to the quality performance. Managing the casting manufacturing to minimize variables and provide a greater consistency with the casting surfaces and the casting condition will realize a lot of benefits. The benefits for parts originate from a thicker layer that is more consistent. The defined anodic structure, pore structure is improved. with the microstructure being more smoother. The anodic oxide layer surface finish offers a brighter surface. You have better color depth, and the hue of color is greater. And there's improved hardness in the oxide layer, which is going to be more resilient to wear interactions in its final application or use. There are quite a bit of benefits for the parts. We've realized that there's improved corrosion resistance from the ability to form the higher thickness ranges, but also the anodic oxide consistency. It avoids the anodic cracking that is common from undissolved or unconditioned intermetallic silicon particles that are not depolarized on the surfaces, and overall higher quality. With a more uniform pore structure and pore distribution, it leads to higher quality, appearance, and performance, which is what the market demands and what the market wants. Additionally, cast alloy benefits to the parts are related to the corrosion performance and the avoidance of failures that occur after anodizing can be realized. With a complex geometry part shape, there's low areas of anodic oxide thickness, commonly referred to as zero spots. The part performance is then degraded. With the proper thickness range, the oxide has good surface profilometry, and that will exhibit a smoother, brighter anodic oxide surface, and that will demonstrate improvements to the oxide hardness and the corresponding wear resistance. These are all the factors that equate to an improved part, a component that is processed through stage 1 and stage 2. Organic dyeing of anodized aluminum parts is very critical. Let's face it, we purchase many things around the home or our office based on how they look, and where a more decorative finish is required, we need to incorporate the full range of cast alloy processing stage 1 and stage 2. The process for cast alloy anodizing provides the ability to improve the color performance, both during the processing of the cast alloy parts, but also when they've been delivered to the end customer or for the final intended end application. As shown here, there's many color benefits to parts incorporating the stage 1 and stage 2 of the process. We can provide a wider range of color options. The higher quality color performance from improved dye penetration into the thicker layers with more pore definition is a very integral, important part. We experience improved resistance to color fading over time, and the depth of color in the palettes, including the black, blue, hue, reds, are important options that are realized for aluminum parts and components. Using stage 1 and stage 2 cast alloy processing improves the sealing performance. The proper sealing of any anodized oxide is the critical part of the success for its intended application. So the sealing steps impact the color performance, but also is important for realizing the best corrosion performance from the anodized oxide coating process. Especially for high silicon casting alloys, higher efficiency sealing improves the performance of the dyes, and it overcomes some traditional problems with the dye process for anodizing. Improvements include longer dye color, retention in service, but also improved dye absorption and less dye bleed during the processing of the cast part is important for the anodizing plant. The greater, higher oxide thickness equates to improved corrosion performance, but only if the oxide is stable, uniform, and consistent, which is what the cast alloy process provides when using stage 1 and stage 2. As a result here, we realize improved resistance to neutral salt spray in lab evaluations, which corresponds to improved performance in field applications. As shown for a 7% silicon cast alloy on the right side photo using the cast alloy process stages 1 and stage 2, it has much higher performance after 800 hours of neutral salt spray compared to not using the cast alloy stages. We experience improved corrosion performance over dye-colored surfaces, generally speaking. So in summary, traditionally anodized oxides for cast alloys require longer anodized process times for producing inadequate layer quality, but the cast alloy process allows for normal production throughput. Additionally, capitalizing on the realized savings of power consumption, reduced energy costs with chilling and other things that we weren't able to discuss during the webinar today. Higher anodized voltages normally required for cast alloys have much less burning tendency with the process, resulting in less rework, improved layer integrity, and overall increased productivity. Post-sealing and dye absorption coloring processes are easier to manage and control. Cast alloy process now allows OEMs, captive manufacturing, job shop applicators working with tier suppliers the ability to anodize with confidence and good performance high silicon, high cast aluminum alloys. Our team is happy to work with you on developing your application for considering the use of high silicon cast alloys. Well, we've come to the end of the webinar. Thank you for attending today. I'm happy to direct you to the right resource in our company to provide parts or more information that would be beneficial for your application. You can see my email address here. Please send me an email if you'd like further information. Again, Brad Durkin, Coventya, thank you very much for attending today. Take care and goodbye for now.
Muchas gracias por tu participación. Aprovechamos este mensaje para compartirte que en AMAS la capacitación técnica es una de nuestras prioridades y además es la misión fundadora de la asociación. Estos programas incluyen principios básicos para los recién llegados a la industria y sesiones en un nivel avanzado para todos aquellos expertos que desean ampliar sus conocimientos. En AMAS nos esforzamos y nos aseguramos de que todos y cada uno de nuestros programas contengan información valiosa y práctica. Queremos escuchar tus necesidades. Compártenos qué programas y temas pueden ayudar a mejorar tus procesos.